Hi, in this video I'm going to go over how to write a report on the production of lead, what the report might look like. In this case the report's going to be in the form of maybe a 60-minute test that might happen in your class. And remember, this is comparing and contrasting the electrochemical and the electrolytic cell. That is a galvanic cell and electrolysis. Now, what's going to happen is if you are being assessed by an NCEA at level 3 or by Achievement Standard 91393, that is the internal redox standard, you'll be expected to write a report on these two processes. So in this example of the assessment, you're asked to write a report on the production of lead, and here we're seeing that we're told that lead can be produced by the lead iron to lead half cell connected to the iron to iron half cell in an electrochemical cell, or using this electrochemical cell here, or lead can also be produced if we were to electrolyze lead iodide liquid here, because it's in molten form. And we have on the actual information we're given at the start, we're supplied with the redox couples or reduction potentials for the couples that we need to know. So they can be helpful in a couple of ways. We've got the couples, so we know what species are going to be involved in our half equations, and we also have the potential, so we can work out the E naught value or the E cell value for each of these cells. So they've given us the cells, and they'll supply us with an observation. Either you're going to carry this out and identify the observation yourself, or in the assessment they'll supply you with the observation. And for the electrochemical cell on the left here, the observation is that the cathode is going to increase in mass. Now remember, the cathode is where reduction happens. Two consonants, cathode reduction, start with a C and an R. And the solution around the anode, and the anode is where oxidation happens, is going to decrease in mass. Okay, it's also going to become a bit more green, but we haven't written that observation down here. Now, if we look at the electrochemical cell, sorry, not electrolytic cell, which is the electrolysis, here we have a molten solution. I know it's molten because we've got liquid next to our lead iodide, and we have a power source attached to it, so it's going to supply electrical energy. We have a pool of silver liquid at our cathode formed, and a purple gas coming from our anode. So that's going to help us unpack each of these. Now, if I'm going to write a report on that, I'm going to focus on one of these at each time, and then finally bring the ideas together and write a concluding statement. So let's, for a start, look at the electrochemical cell. So here's our electrochemical cell. Now, the very first thing we're going to be expected to do, and we need to do this to make sure that we write a report that is going to pass the assessment, Achievement Standard 91393 assessment, is we need to identify which of the couples. So when I mean couples is we have two cells, half cells, in this electrochemical cell. There's a left-hand side half cell. It contains the Fe2 plus and Fe, which will be the redox couple Fe2 plus / Fe, and it contains Fe3 plus, Pb2 plus, and a Pb solid, which is their next redox couple. So we can identify, looking at this cell, what the two redox couples are, and once we've identified the two redox couples involved, the next thing we have to do is identify, of these two couples, which one has the most positive redox potential. Now, what we're doing is we're putting the values on we're putting them on a number series, a number line, I guess. If we have 0 in the middle, and then if we go down, we're negative, we can see here that negative 0.41 is actually more negative than negative 0.13, or negative 0.13 is more positive than negative 0.41. So the most positive redox potential of the couple, and it's only the two that are involved in this electrochemical cell, you have to ignore the iodine one at the bottom, the most positive one is going to be the one that gets reduced. And we need to state that is needed for us to pass this standard. So the reduction potential for the Pb2 plus to Pb is more positive than the ion reduction potential, so it's written as reduction. So we're going to go ahead and write it as reduction. We're going to put Pb2 plus on the left, going to Pb solid on the right, and we are going to balance it by adding 2 electrons to the left hand side, remembering our ion electron balancing method. And if you need any help with that, go back and look at my video on how to balance using the ion electron method. Okay, so that's good. So we have this. The next thing we want to do is let's explain using the gain of electrons here, because this is reduction equals the gain of electrons. That is, we have the saying that Leo the lion goes grr. The grr part is the gain of electrons equals reduction. This is gaining electrons because it's getting them added to the ion on the left hand side. So I'm going to write a statement about this, and I'm going to say that this half equation is reduction as each ion gains 2 electrons to produce Pb solid, right? So I need this statement also to pass this standard. I need to do this statement every time I have a half equation. So we know that this is reduction. I actually don't have to have this statement. I could have this statement or the oxidation number 1. So either of those is fine. So if I want to do the oxidation number 1, of course, I have to do the oxidation number of the species. The lead is oxidation number is +2 because it is a monatomic ion. It has a charge of 2+, and the oxidation number of lead metal is, or solid, is 0. So we can see that the oxidation number is reducing. So we're going to state that, but we're also going to link this equation to the observation. And the observation that we have here is, because this is reduction and it's happening at the cathode, remember that reduction and cathode always paired together because they start with consonants, and oxidation and anode are paired together because they start with vowels. So the cathode is reduction. This is reduction, so this is happening at the cathode. It says that cathode increases in mass. We're going to explain why it increases in mass. Well, it's quite simple, because the lead ions are being reduced to lead metal, and that lead metal is being deposited on the electrode, and we have to write that down. But let's explain about the oxidation number at the same time. So I've written that here. The lead ion is reduced as oxidation of lead atom decreases from +2 in Pb2 plus to 0 in Pb. This Pb solid produced deposits on the cathode, increasing its mass. So this is me. I have linked my observation to the description of how we know, or the explanation of how we know that this changed. This is a reduction half equation. So that's important. We need to do all of these three things again for the oxidation half reaction. Now remember, because we said that this was the reduction half equation, with these couples, the reduction one is always the one written in the forward direction. That is, the Pb2 plus is on the left and the Pb is on the right. But if that's true, if that's the most positive one, the most negative of the couple will go backwards. So Fe will be on the left and Fe2 plus will be on the right. And this is our oxidation equation. And once we balance it, we add these 2 electrons. Of course, this now is going to be losing 2 electrons, because it started off with an Fe solid, but now it's an Fe2 plus ion and 2 electrons that it has lost. So this half equation has lost 2 electrons. Okay, so we can say here that it is the iron solid has lost 2 electrons, each iron solid. So we're going to be specific about that to produce iron 2 plus. Now again, this explaining that this is oxidation, we can do using electron gain and loss, or we can use explain it using change in oxidation numbers. I would suggest you do both, because if you do if you make a mistake in the other one will be your backup. Okay. So now we're going to explain this using oxidation numbers. I've already written the oxidation numbers on top here. Of course, the first the first species on the left, the reactant here, is the iron solid because it is an element. Okay, it has no charge and it's just one type of atom, has an oxidation number of 0. And Fe2 plus, because it is a monatomic ion and it has a charge of 2 plus, has an oxidation number of +2. Now remember, every time I use the word oxidation number, you can replace that with oxidation state. They mean the same thing. So here the Fe is oxidized to Fe2 plus because the oxidation number of the Fe atom has gone from 0 in Fe solid to +2 in Fe aqueous, right? So remember we have to link at some stage our explanation of whether this is oxidation or reduction or to the observation. And if we go down here, we can see the anode, which remember, 2 vowels, anode oxidation, so this decreases in mass, and that makes sense because this iron solid was part of this electrode and now it's become a soluble iron, so the mass has decreased because the iron has been removed from electrode. The mass of the Fe anode will decrease as the iron is reduced to Fe2 plus. Okay, so you could give a bit more explanation to this and say, hey, the iron is turning Fe2 plus, it's soluble, so that's why it got smaller. Okay, so we've done the 2 half equations, we've explained oxidation reduction, and now what we have to do is we're going to have to write a fully balanced equation. Now we're quite lucky here with these two that the number of electrons being gained and lost is equal, so we just need to add these two straight together without having to multiply by a common denominator, lowest common number. So here we add these two together, we cancel out the electrons, and when we add them together, this is our fully balanced equation. So now we've done our fully balanced equation, the next thing we need to do is, what is the E cell for this? What is the E naught value? What's the energy produced by this electrochemical cell? And we can calculate that by doing the following, right? So the E cell here equals the right hand electrode minus the left hand electrode. So we just look at the diagram. Right hand electrode, here it is, minus 0.13, and the left hand is minus 0.41. We substitute them into this equation and then we solve, realizing that that we are subtracting the second value, and if we have two negatives, that becomes a positive. If we have a negative and a positive, it's just a negative. So in this case, we have a positive, so it's minus 0.14 plus 0.41. That gives us a cell voltage here of 0.25 volts. Now we just have to summarize and explain what this means. In this case, what it means is the E cell is positive. Okay, that's fine. As this is an electrochemical cell, the positive value means that electrons flow to left to right. The reaction is spontaneous as it is written. So as we've written the reduction and oxidation equations, it is spontaneous and electrical energy is produced. Now, let's just go over very quickly what each of these bits mean in relation to the grade that we might get. So if you're just wanting to pass, well, you need to identify what is being reduced by the largest reduction potential. We need to explain that. You need to identify what is being you need to explain reduction and oxidation. Now remember, I said you can explain it using gain or loss of electrons, or you can explain it in this first sentence of this next paragraph here. You need all of that to pass. Now that's all you need to pass for this cell. You need to pass the second cell as well. What you also need to do is, if you want to get a better grade, let's look at what you need to do for merit. So for merit, we need to balance the half equations correctly. So if you've written the half equations correctly and balanced, that's one step to merit. The second step to merit is you need to have linked your observations to your reduction explanation and to your oxidation explanation. And the third thing that you need for merit is you need to have calculated the E cell correctly. If you want to get an excellence, well, here's the following things you need to have. You need to have balanced your final equation. You need to have a fully balanced equation. It has to be correct. You need to have made this comparative statement at the bottom. Okay, so in the electrochemical cell, these are the pieces of evidence we're going to look for to give you a grade of achieved, merit, or excellence. Okay, let's look at electrolytic cell then. Okay, let's look at the electrolytic cell here. So the electrolytic cell is the cell where we carry out electrolysis. Remember, there's just one vessel. In this case, it's a crucible, and we have just one, usually one positive ion and one negative ion in the solution. Sometimes there's more than that, and you have to identify which one is going to be reduced or oxidized based on the strength of its redox potential, but in this assessment it's usually more straightforward and we're just given one. So in this case we're given lead iodide. It's liquid because this is molten, so this shape here represents a crucible, which is a piece of ceramic that's heated really hot until the ionic solid turns to a liquid. It's got two electrodes in here, two graphite electrodes, because remember they don't react with the solution, or sorry, with the ions in this I guess it's a molten solution. Notice here that we've got an observation that there is on the cathode here on the right. Obviously reduction is going to happen here because there's a cathode. We have a wee pool of a molten pool here of grey liquid, and on the left we have some purple gas. Okay, so because this is lead iodide, we can see that the two redox couples we're going to be involved interested in are the ones that contain lead and iodide, and they are the two at the bottom, and we're going to ignore the one at the top. Okay, of those two, we can see that the lead one is more negative and the iodine one is more positive. Now when we carry out electrolysis in an electrolytic cell, we are supplying energy, and in this case the redox couple that goes forwards is the most negative, so it's the opposite to electrochemical cell. So the most negative one here is the lead redox couple. So we're going to explain why we chose that in the first place. So because it's the more negative, we're going to write the lead redox couple as reduction, and let's write down the equation. So we have lead ions, because this is an ionic solution, or it's a molten ionic solution. It's got lead 2 plus and I minus ions in it. We are going to turn it into a lead metal. Okay, it's going to be in liquid, and that's the pool of grey liquid that we see here. Now remember, because we've got this half equation, what we can do now is we can explain why this is reduction. We said why we drew it as a reduction half equation because it was the most negative, but let's explain using the loss or gain of electrons. Remembering that Leo, the line goes Gur, that is loss of electrons is oxidation, and gain of electrons, Gur, is reduction. So this is gained electrons. Actually, every lead ion has gained 2 electrons to produce one lead liquid atom. Okay, so let's go on now and do the same explanation. So this is our backup explanation, or it might be the one you're most confident with, is using oxidation numbers. So the lead ion has an oxidation number of +2. Remember, it's a monatomic ion. It has a charge of 2 plus. And the lead liquid here on the right hand side is only made up of one atom. It has no charge, so its oxidation number is 0 because it is an element. So now let's explain this reduction, this equation being reduction, using oxidation numbers. So the oxidation number of lead goes from +2 to 0, +2 in lead 2 plus to 0 in lead liquid. Therefore this is reduction because it's decreased, or the Pb2 plus is reduced as an oxidation number of the Pb atom in is decreased from 2 plus in Pb2 plus to 0 in Pb liquid. Now, we want to link here the observation that we have. This is reduction, so it's the observation at the cathode. Remember, it's reduction, cathode, the two constants go together. So let's find the cathode. Oh, it has a silver pull. That makes sense because lead is a metal. It's going to be a silver color. Why is it going to be a liquid? Well, because it's really hot, okay? To turn an ionic solid into a molten mixture or liquid, molten solution, we actually have to heat it really hot. It's really hot, so it's okay that the lead is a liquid here. So the lead produced from this reaction is formed at the cathode and it forms a silver pull. Okay, that's linked to observation. Awesome. Well, let's do the oxidation half equation now. So if this redox potential went forward because it was the most negative, the other reduction potential must go backwards. So we're going to write 2 iodide. Well, iodide goes to iodine. Now we have to put a 2 here, and this is the most common mistake when people write these halogen reactions, is often they'll miss out the 2 in front of the I minus, and then they'll only put 1 electrons in. Everything becomes a hot mess. So make sure that you remember to balance the number of halogens, in this case the iodines, by putting in 2 in front of the I minus. Let's explain whether this is oxidation or reduction. Of course, this one here is oxidation. We know that because the other one was reduction, but let's justify it using electrons. It's losing 2 electrons. Every iodide loses 1 electron, but we can say that 2 iodides, okay, lose 2 electrons to produce 1 iodine gas. Okay, let's explain oxidation using oxidation numbers. Well, iodide is -1 because it's a monatomic ion, and iodine is an element, so its oxidation number is 0. So we can explain using oxidation numbers, but then we have to link the observations to it. Let's have a look at the observation. This is producing a purple gas. That makes sense because I've written the I2 as a gas. Now, why did I write it as a gas when I wrote it down? Well, because it doesn't say in the redox couple it's a gas, but I can see on here that the purple stuff created here, the stuff created is a gas. And the only thing that's created, apart from the electrons that are lost here, is the I2. So I've put a gas next to it, right? But, so the I minus is oxidized as oxidation number of the I atom has increased from -1 to 0. Take care with this. We are using negative numbers here, and when you start off at a -1 and you go to a 0, that is an increase, even though like you're going from a 1 to a 0. It's a -1 to a 0. And so we have an increase from -1 in I minus to 0 in I2. The purple gas observed at the anode is the I2 produced. I've chucked in the anode here because I know it's oxidation. Remember, anode oxidation. So after we've done all this, we're going to write a balanced equation here. So here it is. Here is our balanced full equation, sorry. So in this case, we've got the lead ions plus the iodide ions. Notice they're in the liquids, remember, because this is a molten solution here. If this was a solution dissolved in water, it would be aqueous, okay? And it's going to make liquid lead because they said it was a liquid, it was a pool here, and iodine gas because there is a gas. Now remember, I knew that the lead was the liquid because it's grey, and the iodine, we might have seen it before in our chemistry class, it is a purple gas color. Okay, so now what's left to do is we have to calculate our E cell. E cell for an electrolytic cell is the reduction minus oxidation. So it's not the right hand minus the left hand electrode like it is in electrochemical cell. It has its own equation. It's just reduction minus oxidation. It's always the R1 first, right? So it's either the right hand or it's reduction. In this case, it's reduction. So I put in the values here. We have minus 0.13 minus positive 0.54. Now, because it's we're subtracting a positive number, it just becomes negative. So it's 0.13 minus 0.54. Two negatives, we add them together, and we get a negative number of negative 0.67 volts. So this is all the information we have to put down for the electrolytic part of our report, apart from we have to summarize it now. And this is a negative value. So this means this electrolytic cell, as it's written here, is not spontaneous. That's what negative means. It's not spontaneous as we've written it. And actually, these are always not spontaneous. The electrical energy that we need for this, so we need electrical energy to make this happen, and it actually has to be at negative 0.67 volts or higher in order to make this reaction happen, because that's how much energy we need to rip those electrons, rip those electrons off the iodide ions and give them to the lead ions. So I need at least that voltage of electrical potential. Okay, so what we're going to do now is we've talked about the electrochemical, we've talked about the electrolytic cell. We're going to just write a a summary of it, a comparison of both of them, and then we've done. That's our report done. Okay, so I said I was done, but not quite. Let's just go over what we need here for passing this. Okay, so again, like the electrochemical cell, we need two things to pass this, but we need to explain why it's oxidation or reduction. Remember, we can use loss or gain of electrons, or we can do increase or decrease in oxidation number. The other thing that we need to say here to make sure that we pass is that we've calculated a negative value for our E cell and it's not spontaneous. Now, if you stuff up your calculation here, that's fine, as long as you say the electrolytic cell is negative and it's not spontaneous. It's always negative and it's always not spontaneous. To get a merit, same type of thing, we need to write the two half equations. They have to be correctly balanced. And then we have to make sure that our observations are linked to our description, our explanation of oxidation reduction. And lastly, we need to calculate a correct value for our E cell. If we want to get an excellence, if we're aiming for excellence here, we need to make sure that our full equation is balanced correctly and that we've made a good summary at the end here, and we've said, look, this requires electrical energy. It needs at least negative at least 0.67 volts for this reaction to happen, and the reason is it's not spontaneous and it needs it, and that's the other bit we need for excellence. Okay, let's let's get to the overall comparison that we're going to write. Okay, so this is information still going to be on top of our slide, and overall we're going to write the following in our final summary of this comparison. And what we're going to say is both electrochemical and electrochemical and the electrolytic cell can produce lead metal. And both of these cells, remember it said compare and contrast how they'll produce lead solid. Well, they're not producing lead solid, they're producing lead metal, right? How will they produce it? Fine, because they both reduce the lead ions to lead metal, right? So that's something that's similar about them both. Now what's different is the electrochemical cell is spontaneous. It's always spontaneous, and it produces electrical energy, where the electrolytic cell is not spontaneous and it needs electrical energy to be supplied. Now this might be negative if you wanted to make lead. Of course, you're going to have to find some external power source to make this reaction happen. And the last thing I guess we could say in a comparison of these two is the electrolytic cell is a lot less complex. It's just one vessel, right? It's one container, 2 electrodes, and we've actually got one solution of ions. Okay, it's either a solution of ions or a molten solution. So electrolytic reaction can be carried out in one vessel. Well, the electrochemical one is actually a lot more complicated. We need a salt bridge, and we need 2 separate vessels and 2 separate solutions. So you could argue that, I guess you could argue that either one of these is better. The electrolytic one is better because it's less complex, even though you need to find an energy source to provide your energy. Or you could argue that the electrochemical one, hey, you don't need extra energy apart from you just grab the 2 solutions, you put it all together, and hey presto, you're going to get lead metal produced. Okay, and that there is the end of the video, and that's how we go about writing a great report for the Achievement Standard 91393 assessment. Okay, good luck with your test.